Welcome back to our next lesson, chapter 4.3, Gravitational Fields. A couple of points. You can see I changed my color to blue this time. But also I didn't do a video on chapter 4.1 because it's a relatively short section and usually you can just read that section of the text pretty quickly to pick up the main ideas of what's going on there. Alright, let's get into it. So let's have a think. First point there. What direction would a ball fall to Earth if the Earth was flat compared to spherical? So you'd think on my little diagram in the middle here, on a planet like this, the ball would fall straight down no matter where you were on Jupiter, on that globe there. But on a flat Earth, like this one down here, the ball wouldn't fall straight down like that. It would fall to the center of the Earth's mass, because balls don't fall down, they fall to the center of the mass. Okay, so on a flat Earth, if you're standing over here, a ball won't fall straight down, it would fall across to the center of the mass of the Earth. Next one there, did Newton discover the laws of gravity or did he invent them? Well, he's derived them from the mathematics. So he's basically the first one that, you wouldn't say he invented gravity, but yes, he developed our understanding of it. Third question there, you probably come across already. What keeps things in orbit? Why doesn't it crash to the ground? It's a function of the velocity of the object sideways and the mass. The mass is moving sideways in a gravitational field. It's falling towards the Earth, but it's falling sideways. And over the side here's a nice little picture from Spaceballs with the giant maid, where she turns the vacuum cleaner from suck to blow. It's an old early 90s movie called Spaceballs. Highly recommended viewing. Alright, what's the point of today? We're going to look at the gravitational field's strength. Okay, we're not really looking at G in terms of gravitational acceleration. We're looking at the gravitational field and the strength within that field. So we're going to do some calculations and so on with this, like we always do because it's physics. Okay, so what's a field? So let's come back to another dead white guy, Michael Faraday. In around 1850, he came up with the idea of calling something in science a field. Originally, what he thought was, well, let's look at magnets and electrics and so on. The field kind of looks like a field as in a paddock where there's animals grazing and stuff like that. So that's why he used the term field. It's kind of like when Mendel first described cells in living organisms. He thought that looked like a cell that a monk lives in. A monk's room was called a cell, so that's why he used that term, because it looked kind of similar to him. Faraday thought, well, there's an effect of the magnet or an electric force going across a certain area. It kind of looks like a field, or we could visualize it like a field, so that's why he used the term field. Now we're talking about gravitational forces, and the same term was applied to that sort of area. But what do we mean by a gravitational field? Let's consider this example here. If you think of a three-dimensional map of your room, of the temperature in that room, in order to work out a temperature field map, you would have to do thousands of measurements three-dimensionally throughout that room of the temperature at various points all throughout that room. And that would form your temperature field. Think about the question I've asked there. How would a Bunsen burner affect this field? It's going to add a point of temperature in that room, which will start to influence the temperatures around that room. It would change the temperature field. And that's a good analogy for gravity. So the field is the region of space where these forces are experienced. The Bunsen burner in our analogy would be like a huge mass, like a planet or a star, that changes that field in that region. And we say in that last point there, the force is described as it's mediated or brought about by the field. It's kind of a funny concept really, but we have that field with those properties of gravity and we can map how it changes throughout that area. Here's a little question here, a little challenge for you. Pause the video, have a quick read about that. Think about how you're standing on scales. Seriously, pause it and read it before you listen to me explain it. You're standing on those scales. There is a normal force and your force of weight going down on there. If you bend your knees, your weight sitting on that scale will decrease. So that should therefore decrease the pressure that you're putting down on the scales. And there's a nice little meme inside there for you. All right, so a bit more about gravitational fields. Gravitational field, it's basically, think of the gravity, it's a vector, so it's got a direction that applies to it. On Earth, we often say that that direction is down, but as I mentioned a couple of slides back, it's not down, it is towards the center of the mass. And the center of the mass of the Earth happens to be straight down compared to where we are standing here on the Earth. And no, people on the bottom of the Earth, like in Australia, are not walking around their heads. We are standing on the Earth like the people on the other side of the Earth. It's just that the gravitational field is pulling us down towards the center, much like people on the other side of the Earth. All right, so Einstein was the one that really expanded on Newton's work and developed the idea of how we actually understand gravity. And the interesting thing here is 1915 was when he was doing that, so a little bit over 100 years ago when I'm recording this video. Think about the little bubble I've got at the top there. We think that anatomically correct humans are 200 or 300,000 years old. Think about what percentage of human history 100 years or 102 years is, 103 years, sorry, out of that 200,000 years. See if you can work out that percentage. All right. The interesting thing about the electrostatics and magnetics is they were the ones that Faraday started referring to as fields, and the mathematical relationships of them are a similar relationship mathematically to gravity, but the way that gravity manifests itself is a fundamentally different idea. Gravity is what Einstein really took a leap on in terms of our understanding and said it's this distortion or a warp of space itself. It's not really a force of attraction like a magnetic north-south pole force of attraction. It's an actual distortion of the space around that mass. In that last point there, we've never actually observed anti-gravity. It's been theorized. Think about the little cloud over the side there. What would anti-gravity look like? Stop and have a think about that before you play this video further. Go on, stop it and think about it. If gravity is a force attracting two objects towards each other, anti-gravity would be a force pushing them away from each other. We've never seen it, we've never observed it, we've theorized it may exist, and who knows, it may exist, we don't know. We theorized what black holes were before we'd ever actually detected one. Maybe it does exist, maybe dark matter plays a role, but get back to one of my little favorite questions over here. What does dark mean? Dark means we don't understand it. Yeah, maybe there's this matter that exists, maybe it has this property. What would it look like? We don't really know. How would it behave? We don't really know. So we'll just call it dark. Dark means we don't understand it. All right, so I've said this point a few times. The gravitational field is towards the center of mass. It is not down, it is towards the center of whatever the mass is. And that's what these two images are trying to show you. And you can see the field lines point towards the center of the mass in both of those scenarios there. All right, so let's think in terms of this gravitational field strength that I've listed up here. So that's what we're calling G. It's basically a net force per unit of mass. How is this related to our Newton's second law, F equals ma? G is this guy here, and it is a proportional relationship between the force and the mass. The gravitational field strength is that force and the mass. This little map here on the right hand side, there's one I've put in here. Basically what it shows is that the force of gravity, the gravitational field strength on planet Earth, changes across the planet. You can see that we've sort of got more gravity, less gravity based on the colours here. So the question becomes, well, why is there more gravity in those places and less gravity in other places? It's basically due to mass. The gravitational field varies because of the mass of those areas. Think about something like India in here. What's India doing? India's sitting on a plate that is moving forward. So it makes sense that it's pushing up a lot of mass here above it. What does that say about this reduced gravitational field strength behind it? That's on the surface of the Earth, but think further down below the surface of the Earth to where more mass actually lies underneath the surface of the Earth, in the crust of the Earth. All right, physics, so here's our nice little formula. And it's a little bit of a derivation of the one that we had last time. Okay, we're working at the gravitational field strength, not so much the force of gravity like we did in the last lesson. We have our gravitational constant. We have the mass of the larger object. Now, because we're referring to the gravitational field strength, it's like calculating 9.8 meters per second. Okay? It's a function of how far away you are from that point of mass. So what is your force of gravity is related to how far away you are from that force of mass, and there's a constant involved as well. That's what this is telling us. So G is the strength of the gravitational field. Big G is our gravitational constant. The mass of the larger object, as in the larger object like Earth, your mass doesn't matter because you're so small and insignificant compared to the mass of the Earth. And how far away are you from that Earth? So it's all about your force of gravity is about how far away you are from that massive object. Now, technically our units are newtons per kilogram, as in it's a strength of the field, which is a force in newtons per kilogram that it is affecting. But that can be shown to be an acceleration, which is meters per second squared, which is like when we talk about the acceleration due to gravity being 9.8 meters per second squared. If you check out page 128 of the Walding textbook that I'm referring to for all these videos, it'll have a nice little derivation of that, which will either thoroughly excite you or put you to sleep at night. Righto, so here's a question. Let's have a go. Calculate the gravitational field strength 10,000 k's above the Earth or at the surface of the Earth. Now, what do we expect? We expect that the further you move away from the Earth, the less will be your acceleration due to gravity. The less will be the strength of that gravitational field. Notice how I'm starting to use those terms. So, once again, what was the formula? I had it on the previous slide. Can you write it down before we do this? That's your formula. So it's pretty much a straightforward matter of plug those numbers in and it'll all come out in the wash. And here's our solution. So what are our facts? So the distance away from the Earth is 10,000 kilometers, or that one there. The mass of the Earth is a constant. It's not going to change. So that's a number that you get given when you do these questions. You wouldn't be expecting to remember that. And we've got to find G. We also know big G is another constant that we get given. So all this stuff on top of the equation we get given. Notice what we've done. We wrote down our what we knew here to keep our thinking right. Picked our formula, wrote it down, plugged the numbers in, comes out in the wash. 3.98 meters per second. And you would expect that the further you are away from Earth, the less is the gravitational field. In part B, on the Earth's surface, this one we're doing slightly different. The only thing we're changing is we're not talking about 10,000 kilometers above Earth's surface. We're talking at the surface of the Earth. And in this scenario, we're working out what is our distance from the center of Earth. And when we do that one, 9.8 meters per second squared. Don't forget, you're talking about a vector quantity. You need a direction as well. Okay, let's have a look at this little image here. Ignore the cat over on the side there. The direction of the gravitational field points towards the Earth's surface. This is the direction, so how can we say this a different way? The Earth's gravitational field is a force. It's pointing towards the surface, but what that force is doing is acting on an object. So if I can say this sentence again, but more completely, the direction of the Earth's gravitational field points towards the Earth's surface. This is the direction of the force acting on an object in that field. Just think about that. This is the direction of the force acting on an object that is in that field. All right. So what I've got here is a table of Values for g, acceleration due to gravity within that gravitational field, and distance from the Earth's surface and the Earth's centre. Okay. Now, you can see that g decreases, and what's happening to our distance? Our distance is increasing. So, think about my question here. As you double or triple the distance, what happens to g? And remember, let's go back to our equations. What are we looking at in this thing here? We are looking at this term here and this term here. It is an inverse square relationship. This gets back to what I spoke about in the last lesson. Think about how, if I change one of those two, what's the implication for the other one? This is the type of thing you need to be doing in your data test. It's a skill you'll need to be doing to get through this course. Look at your equation, think, right, if I change one term there, what is the effect on the other side of the equal sign? Okay, so gravitational field strength inside Earth. So what we're looking at here is what is the gravitational field inside the planet. Now, the thing about our planet is there is this core that is quite solid. All right, usually an iron sort of core, very, very dense. So what that means is that if you're standing here on the surface, like this bloke here in the middle of the ocean, what is your acceleration due to gravity? It's 9.8. But as you start to go down through the surface of the Earth, yes, there will be mass above you, but you are getting closer and closer to that very, very dense core. So the force of the gravitational field will increase, your acceleration due to gravity will slightly increase as you reach this mantle core boundary, and then it'll rapidly decrease. Obviously, once you pass this point here, as you enter into the Earth, you start to have far more mass above you than below you, until you get right to the middle where you are weightless, as in you are at the centre of the Earth's mass, and hence your distance away is 0. Go back to your equation. If your distance becomes 0, what does that do to the value of g? That's what I said on the last slide. Understand the difference between and how those two relate to each other. All right. Little point here. It takes about 42 minutes to fall through the Earth. All right. So if you could drill a tunnel all the way through the Earth like this, and you stood at one end and jumped through to come out the other end, it would take about 42 minutes to fall through, which is quite ironic, the meaning of life, the universe and everything. In the movie Total Recall, they had an example of doing this to travel from one side of the planet to the other. Very bad version of Total Recall. Remakes are often worse than the original. The original with good old Arnie was way, way better. But anyway, I digress. My question here, why is this difficult? Basically, it's due to what's called the Coriolis effect. If you're falling from pole to pole, from the top of the Earth to the bottom of the Earth is spinning around you. If you were to look from the top of the Earth, there's a hole that you're falling through, and the Earth's rotating around you, and you just go through that hole in the middle. If you look at the Earth from the side, it is a case of a hole through the Earth like that. Sorry, that's a badly drawn Earth. All right, the Earth is rotating around you, and you simply fall straight down through there. If your shaft that you're falling through is on an angle like this, the problem we have is that as you start to fall, the Earth rotates. So as on that blue shaft that I drew there, you start falling down, you're here, falling down there, but the Earth's rotating, you are not. So hence you will get smeared down the side here, and we find a nice really red bloody colour, because that's probably how you'll end up. Okay, let's look at weightlessness in space. So another dead white guy, Jules Verne. Back in 1867, he wrote a book called From the Earth to the Moon, which was about a trip, obviously, in a rocket from the Earth travelling to the moon. Now, Jules Verne was interesting in some of his books because he had a lot of sort of detailed calculations of a lot of different things. He wrote another book, 20,000 Leagues Under the Sea, which was basically about a submarine travelling 20,000 leagues under the sea. He had quite detailed calculations as to how a submarine could operate underneath the ocean, underneath the surface of the ocean, and how it could create enough oxygen for people as well as energy to propel the submarine forward. I used to think 20,000 leagues under the sea referred to the fact that it was that distance below the surface of the ocean. But 20,000 leagues is, it's over 100,000 kilometres, I believe. It's a long way. 20,000 leagues under the sea refers to the submarine travelling that distance under the surface of the ocean, not that distance below the surface of the ocean. Now, in his book From the Earth to the Moon, he did some quite detailed calculations about what he theorised was the Earth has a gravitational field, the Moon has a gravitational field. There must be a point partway between them where we work out the gravitational field of Earth and we work out the gravitational field of the Moon. When those two equal each other, the force of gravity that is pulling you towards the Moon is the same as towards Earth. It's obviously a lot further from Earth because the mass of the Earth is so much bigger, hence the gravitational field force is so much bigger. But at that point there, you should be weightless because those two vectors will cancel each other out. There are obviously other factors to be considered here. There's the sun that's having an effect on your gravitational field, other planets and so on. Okay, but in this little isolated example, that point in the middle there, the two forces cancel out and you would be weightless. Think about my point up here. It's all related to Newton's second law. All right, let's look at some examples, and don't be like this bloke over the side here. When gravity gets too much, how do you increase the gravitational field force? Think about what it's a function of. It's a function of masses and distance. So you either get more mass or you get less distance. What is the equation I'm referring to when I do that? We did it. We talked about one version of it. We talked about it last lesson. Okay, what happens when mass increases to a point that the gravity is too large to overcome velocity? All right. So when mass gets so big that your velocity moving away from it is just not enough to overcome the gravitational field, you can't escape ever. Think about it. What do we call this sort of scenario? When there's something so massive, so much mass that you'll never get away, we call it a black hole. Now, although we theorised these, it was only in 1972, the end of 1972, that we first had tentative evidence of a black hole. We'd theorised about it for quite some time, but that was when we first had evidence. And I know 1972 feels a long time, like it may as well be ancient history if you're in grade 11 or 12 at the moment. But really, in the big scheme of things, it wasn't that long ago. Don't forget what I've mentioned earlier. Anatomically correct humans, as in humans that look just like us, are about 200,000 years old, give or take. So, Cygnus X1 was the first black hole that we sort of had evidence of. Look at this little diagram here. You can see the Southern Cross through there, and there he is right there. It's just off to the side of it. So you can look up in the night sky and see it. April 2019, we got our first image of a black hole. We had little sort of theorised artist impressions and all this sort of business in the past, but that was our first actual image of a black hole. Why does it look a little bit weird? It's kind of funny because you've got a round mass, and if you're looking at it from a particular angle, the light from behind gets warped around it as it comes around it. All right, and that's why we sort of end up with this bright ring sort of structure along there. All right, so a bit more about black holes. Black holes, we think, are at the center of all galaxies. There's lots of good evidence for that. Usually we measure the black holes in terms of solar masses. You can't really measure it in standard units too easily because kilograms, if you try and work out the mass of the Earth, it's huge, and you've got a lot of decimal places or a huge exponential number. The mass of the Sun is huge, and the mass of Earth is insignificant compared to the Sun. So we've referred to our sun's solar mass, and how many times is that? Now, black holes are, we have this sort of point that we call this Schwarzschild radius. Another way to think about it is the event horizon. All right. Think about our little figure 8 on the side here. We have this radius, which is this outer event horizon point. The event horizon is the point. The distance it is out from the black hole is what's called the Schwarzschild radius. I can't pronounce that properly. And that's the point where you can see here these objects moving past, whether it's light or matter or whatever, they're bent because of the acceleration caused by the gravitational field. But this bloke here is not so lucky, and he continually spirals into the centre because he's inside the event horizon, inside that Schwarzschild radius. He will never get out. He's going into that black hole, and that's it. Nice little fact here. If an object like a black hole had 10 solar masses, as in it was 10 times the mass of our sun, the radius of it would be 30 kilometres. If you go within 30 kilometres of that object, you will not get out. Alright, so think about my question here. If we've got this massive black hole in the middle of our solar system, our galaxy, the Milky Way, why don't we get sucked into it? Now the thing here is there's massive distances involved. Huge distances involved. The Milky Way, the whole diameter of it, from one side to another, is about 150 to 200,000 light years. A light year is probably a little bit too inconceivably large to get your head around. The distance light travels in a year, it travels 300,000 kilometres a second. 200,000 of those is the distance across the Milky Way. We reckon there's somewhere between 1 and 400 billion stars in the Milky Way, and probably about 100 billion planets. Most of them are not habitable, but the odds are in 100 billion planets, there are plenty that exist within this nice zone, the nice distance from the sun, what we call the Goldilocks zone, where you have liquid water on the surface, it's not too hot, it's not too cold, those sorts of things. Now, our solar system, where we've got the sun pointed out here, is about 26,490 light years from the centre of the Milky Way. That's why we don't get sucked in. We're 26,490 light years away, give or take 100 light years. This the bulge at the middle of our Milky Way, and you look at it from side on, the Milky Way looks a bit like a flat disk with a bulge in the middle here. That bulge there is about 10,000 light years across. And we reckon right in the middle here is Sagittarius A, which is a supermassive black hole of about 4.1 million solar masses. Stars orbit about 220 kilometres a second. Alright, so think of us as travelling around here, I can't recall if we're clockwise or anti-clockwise, at about 220 kilometres a second. I suppose it's clockwise or anti-clockwise depending on which way you're looking at it. It takes us about 240 million years to do a lap of the Milky Way. Dinosaurs died out about 60 million years ago. Dinosaurs we first evolved about 160 odd million years ago. It takes about 240 million years to do a lap. So in the time we've done one orbit of the Milky Way, dinosaurs have long since come and gone from this planet. We're talking huge timescales and massive distances. The other thing we think is that the Milky Way is moving at about 600 kilometres per second through the universe. With respect to the other matter around us, that's our estimate, 600 kilometres per second. So we're travelling 220 kilometres per second around the Milky Way, and it's travelling 600 kilometres per second through space. Huge distances, huge numbers involved here. Alright, let's wrap this up. There's a nice little video there. You can pause, type that into YouTube and check it out. We've been talking about the gravitational field strength there, and I think we've covered a lot of that and some extra stuff. Now, here's a challenge question for you. Think about what we did in last chapter where we spoke about circular motion. And now we're talking about gravitational fields. Sorry, not last chapter, chapter 3. Chapter 3 of the book, we're talking about about circular motion. Now here we are in chapter 4. We're talking about laws of gravity. So just pause what I've got here and just have a look at that stuff on the screen there and see if you can start to combine some of these things together. I was just talking about us traveling 220 kilometers per second around the Milky Way. Go back to your formula that we used in chapter 3 and see if you can start to work out some unknowns. See if you can work out from, the radius that we're traveling in, the force involved. Go and find those equations, plug in what you know and see if you can work it out. Here's a nice challenge on the screen here about binary stars. A binary star is two stars orbiting around a common center. Often we refer to as multiple star systems. This sort of example here, you could have two stars sort of like this one here orbiting around this path and the other one orbiting around the other path. They could be just spinning around each other like this sort of scenario. You could have three stars, perhaps two orbiting around each other, and then they are orbiting around with another star. Can you combine your understanding to explain how these objects are moving around each other? Can you combine your understanding of circular motion with the gravitational field to try and get an idea of what the forces are and where the forces are acting to keep these two stars orbiting each other? Now let's have another real challenge. Here's a nice little video here you can watch about the closest star system to us, which is, we say the closest star to us is Proxima Centauri, but it's basically the Alpha Centauri system. All right. Down here I've got a nice little size comparison for you. There's our Sun. So Alpha Centauri A is a bit bigger than our Sun. Alpha Centauri B is a bit smaller than our Sun. And we think that those two are orbiting each other, but then Proxima Centauri is a lot smaller and he is orbiting them. So here's A and B and here's Proxima here. Now, Proxima is going to go all the way around to the other side here and be further away, Earth over this side. So it will eventually be further away from us. But at the moment, if he's over here on this side, he is the closest star to us. So here's a real challenge if you're planning on trying to get yourself towards an A-level response. Can you describe what is the forces holding Alpha Centauri A and B in orbit of each other? Think of here's A, here's B orbiting around him. And can you then try to quantify or try to understand using your circular motion equations and your gravitation equations what are the forces keeping Proxima orbiting those two? And that's our closest star system to us. Alright, so don't be like this bloke here and look at memes or draw glasses on pictures, guys like these. Alright, get on with 4.3, get on with the chapter review, and I've summarised the equations that we've used in this chapter there for you, just to be nice. Okay, thanks for coming.